In most cases, plastic deformation in metals occurs by dislocation motion. However, under certain conditions, plastic deformation can occur by deformation twinning instead. So this slide shows schematically the difference between dislocation motion and deformation twinning. It's worth pointing out that this is just for a single crystal, but of course both occur in polycrystals as well. So in dislocation motion, that occurs by the movement of many dislocations along slip planes. And so this doesn't show individual dislocations, it just shows that the net effect is that we have different regions of the crystal displaced with respect to each other. Deformation twinning, on the other hand, occurs by the cooperative shear movement of many atoms. All of the atoms, they move at the same time in the same direction, and that direction is the twinning direction. So the net effect is that we recreate the same crystal structure here in the middle, but just in a different orientation. So the bit here, this is a twin, and it's got the same structure as the parent structure, but reflected across the twin boundaries. It's worth pointing out that if this structure was different to the parent structure, then this would have been a martensitic transformation. In this demonstration, we're going to illustrate deformation twinning using these two bars of freshly cast tin. So tin has a tetragonal crystal structure, which is a much lower symmetry than most metals, which makes dislocation motion more difficult, and therefore favours deformation twinning. So I'm going to take one of these bars, and I'm going to heat it up using freshly boiled water. So I'm going to leave that there for just a little while, and in the meantime I'm going to take this bar that's just at room temperature and I'm going to bend it. And I'm going to do that quite close to the microphone, and you should be able to hear why in a second. So now I'm going to take the one that's been heating up and do exactly the same thing to it. We'll consider the room temperature case first. When I bent the bar, deformation twinning took place, and we heard a characteristic crackling noise known as tin cry. The reason we heard this noise is because during deformation twinning, the atoms move very rapidly, all at the same time, which generates a sound wave. So this is illustrated schematically in this very simple animation. When we press start, a twin will be formed, the atoms will move, and a sound wave will be generated. You'll have noticed that no noise was generated in the sample at 100 degrees. The reason for this is related to the relative ease with which deformation twinning and dislocation motion take place. So this is illustrated schematically in this slide, which plots the critical stress for each type of deformation to occur against the temperature. Dislocation motion is thermally activated, so you can see that it occurs much more easily at higher temperatures. Twinning, on the other hand, is almost independent of temperature and can also occur at high strain rates. So therefore, twinning tends to be favoured at low temperatures and high strain rates. So in our tin sample, the one at room temperature, we saw that deformation twinning dominated, so we must have been down here somewhere, whereas in the sample at 100 degrees, dislocation motion was favoured.